everyone. I'm Josh. Haley is also here, and I want to give two prefaces before I start. First is I'm not a salmon person. Haley was the salmon person, so my apologies if I mess up any salmon biology that goes on here. The second thing is that I'm going to be talking about time series models. Those are also not my model of choice. It's the first time I've ever used a time series model for anything of note. So if anyone is looking for an in-depth discussion of time series models, I'm not the right person to ask deep questions of. So I will give a very basic overview of them, but we will stop there. So Haley gave a presentation earlier in the week about the Ricker-Stuck recruit model, which is kind of the basis for what we did here. So briefly to recap, the base Ricker model before it's been linearized essentially looks like a dome-shaped recruitment. So you have some relation between the number of spawners in the population and the number of recruits, and there's some intermediate number of spawners that leads to the maximum number of recruits. And then as you get too many spawners, density-dependent effects take over, and your number of recruits declines. Luckily, the way it's written, you can reparameterize it into essentially a linear regression in terms of coefficients A and B and the number of spawners. And this is really useful because this is very easy to fit in a quantitative context, and then use that to get estimates. And then once you have spawners, you get estimates of recruits for upcoming years. So that's the quick intro to stock recruit models. As a quick overview for time series models, there's typically three things that we want to think about when we are building a time series model. The first is whether or not there's autocorrelation present in our data set. So autocorrelation is essentially just how correlated are individual observations across time lags. So is your current observation really well correlated with observations 1 time step ago, 2 time steps ago, 3 time steps ago, etc. The other thing we'd like to think about is seasonality. So are there trends that repeat regularly with some periodicity? So do you have like a nice sinusoidal looking pattern over time? And then we also want to think about stationarity, which is generally are seasonal trends changing over time. So do you get essentially, like in the case of salmon, do you get returns steadily going up across time, so are they steadily going down across time, or are they kind of fairly stable? So there's lots of different time series models. The one that we're going to talk about that we use is called ARIMA, so it's an autoregressive integrated moving average model. You'll frequently see them written in the literature like this. So they're parameterized with P, D, and Q. I'm not going to go into what P, D, and Q are because I don't fully understand what P, D, and Q are. What I can tell you is that P is an autoregression parameter, so it defines how much autoregression is present in your time series model. D is a differencing variable, so you can take like the difference between like time step 1 and time step 2 or time step 3, and that sometimes gets rid of some seasonality problems. And Q is a moving average parameter, which essentially tells the model how you want to smooth through data. So I think a 1 is there's no smoothing, 0 is no smoothing, 1 is like a standard moving average, and then as you increase Q, you get into like exponential moving averages that discount really old observations in favor of newer ones. So this equation here is the very generalized form of what an ARIMA model looks like. So those first few terms, phi 1, y t minus 1, those are all your autoregression terms, and then theta 1 times e to the t minus 1 are all of your moving average terms. So essentially this is a very long linear equation to get this. So what we actually did here, so there's essentially 5 steps. So the first thing we do is we compute and forecast return proportions by age for each stock. So that's what this plot is here. So essentially all of these lines are the proportion of returns across forecast years that are each age. So age 2s are red all the way through age 7s in pink. So by and large, most of our returns are ages 4s, 5s, and 6s. After we have the kind of forecasted return proportions by age, we go ahead and compute linearized Ricker model parameters and use them to fit a Ricker-Stuck recruit model. And then we go ahead and calculate residuals from that Ricker model. And then we fit a time series model to those residuals. So what this allows us to do is we fit a standard stock recruit model, and then we try and look for patterns in where there's error between the Ricker model and the actual true returns. And then we forecast future returns based on the Ricker model that we have, the forecasted age proportions, and then the time series fits to the residuals. So what I'm going to show here is just 5 stocks, so we're not going to show all 14 because most of them aren't terribly interesting. So the one on the top left is a weird case, so that is the one Columbia River system stock. We actually don't do a effective time series there because we were lacking return proportions by age. So that is essentially just the direct output from running a linearized rigor fit. For the rest of these, the red line is the actual true total returns calculated from the data, and blue is what our time series model went ahead and predicted. So we can see a few things. First one is in the bottom left. So stocks with that kind of extreme periodicity are really well fit by time series models because they're exceptionally regular. So the time series models pick up on the seasonality really, really well. And you see that in some of the other Fraser stocks that have really good periodic trends. The other ones that we can see in number 2 and 3, those tend to have what we call like a directionality trend. So they tend to be, it looks like returns have steadily been increasing over time. If you squint a little bit at them, turns out the time series models also fairly effectively pick up that kind of trend over time, which is nice. Something that just a standard rigor model isn't necessarily going to pick up. And then the big block points are what our actual forecasts for 2024 are. So these were kind of some interesting case studies. By and large, a lot of these time series models don't tell us anything. So a lot of the time series are very, very stationary. So all of the time series models revert into just kind of a long-term average. So they just assume that the prediction is essentially going to be just the rigor model fit with some very, very small deviation from that. So kind of in conclusion, generally return proportions by age are roughly stationary. That's really nice. If they weren't, these models get really complicated. Residual patterns are stationary a lot of the time, particularly in Bristol Bay. A lot of the residuals are very kind of nicely behaved. They're a lot less stationary in the Fraser River stocks with those strong periodic trends. And time series methods seem to pretty adeptly work for stocks that exhibit those strong periodic trends. Now, are time series models an improvement over other methods? Probably not. They seem to be at least vaguely competitive. The one thing that is nice about them is that they're really simple to implement compared to things like some of the other models that we've seen that take a lot of covariates. This had no covariates. This was just very simple model that ran in seconds, and then spawning data and recruit data. That was it. So it's very, very easy to parameterize. If you want to get into it, you can add covariates to time series models. The models take longer to run, and you start to get into some weird variance problems. But you can do that. There's lots of other variations of time series methods that are probably more adept to this data. This was a very simplified example, given what the amount I knew about time series methods at the time.